Hello, my name is Matteo Galossi and I'm here to present Lab 2, Lines of Charge. The purpose of this experiment was to construct a physical and computational model to approximately determine the amount of charge on each tape necessary to float one above the other. This lab is really a continuation of Lab 1 with one key difference. The tape is assumed to be a line charge rather than a single point charge concentrated in the middle of the tape. Some key assumptions we made was that 1, each charged tape created had the same charge. And then 2, the charge is evenly distributed along the length of each U-tape, having the same amount of charge across each tape. The fundamental principles involved were Newton's second law, which is related because the tapes did not experience any change of momentum. Thus, we could conclude that the net force on each tape would have to equal 0. The second principle was the Coulomb electrical force. We know that every electric charge exerts a force on every other electric charge. And this principle lets us know that like charges repel each other while opposite charges attract each other. And lastly, the principle that had to do really well with this lab was the principle that has to do with electric fields of distributed charges, considering that the tape was considered to be a line charge, with charge distributed among the entire length of the tape. So in order to do this, we had to divide the charged tape into a series of point charges, and then we found the electrical field of a typical piece due to one point charge. And then we summed the electrical field of all the pieces to find the total charge. Now for our methods, measurements, and results. We first had to charge two pieces of tape by quickly ripping them apart and observe the interactions between each other and on other objects such as a negatively charged pen. When we brought two tapes together, the tapes repelled each other, which is expected as like charges repel and opposites attract. But when we brought the tape next to a negatively charged pen, we saw that it attracted the pen. Thus, we were able to conclude that the tape was a positive in charge. Next, we had to find the separation distance between each tape, which is the distance between the two tapes as the top tape began to float. And lastly, we had to calculate the charge using the computational model. We know that net force must equal 0, and we know that the two sole forces on the top tape are the gravitational force and the electrical force. So we were able to calculate the gravitational force first, and we knew that the electrical force would equal this in magnitude but opposite in direction. And some of the fundamental equations used are as shown. Now, for the measurements and results. We have the length, mass, and separation distance within the tapes that we were able to measure and calculate. And now, in Lab 1, we found the charge of a tape as a single point charge concentrated in the middle, and we found it to be 7.38 times 10 to the negative 9th coulombs. While in Lab 2, this lab, we considered the tape as a line charge, and we found the charge to be 9.6 times 10 to the negative 8th coulombs, which is significantly bigger. The results were obtained by using the charge of tape calculated in Lab 1 as a starting point for the computational model. In order to find the charge in Lab 2, we had to increase the charge until the magnitude of the electric force and force of gravity were equal. These two values had to be equal and opposite. So the further we increased the charge, the output was able to show us how close we were able to get to the magnitude of gravitational force. So in the model to our right is our output and result of Lab 2. The red spheres represents the top tape. The blue spheres represents the bottom tape. The white arrow is the electric force on top tape due to the bottom tape. The yellow arrow is the gravitational force on the top tape. And the green arrow showcases the electric field at each piece of charge on top tape due to bottom tape. Now, this is the computational model itself. The first part of this model, on the image to the left, defines the electric field and defines the tape as a single line charge. And then, the image to your right calculates the electric field and force at each point of the line charge. The code iterates through each point on the top tape and calculates the electric field and force caused by each point on the bottom tape. And then superimposes this and sums up all the charges. Now, finally, for some additional questions. So let's say you had modeled each of our tapes as a single point charge, like in the previous lab. Comparing the estimated value of the charge, what we'd get with the experimental data to produce a point charge model to the value you got with your line charge. So let's say if we modeled it under a single point charge, the value for this charge would be less accurate when compared to the value of the line charge model.
the charge would be smaller as the area is more concentrated, which is shown by our values. The point charge is 7.38 times 10 to the negative ninth, while the line charge is 9.6 times 10 to the negative eighth. These estimates differ because the line charge better models the actual shape of a strip of tape, thus it is more precise. The difference in shapes of the charges creates a difference in the estimates calculated.